Welcome to lesson 5.07. Here we're going to be fitting an exponential function to a data set and then using that function or model to answer some questions about the situation. So let's start with this problem here. Go ahead and copy it down along with the table, and in as many ways as you can, describe why an exponential function would be able to model this data, or why this data here seems to be created by an exponential function. Okay, so if you were struggling there, I'm going to give you a hint or two. I want you to go back and think about the example that we started this unit off with, which was the grains of rice doubling, and think about how that allowed us to construct an exponential function, what the key characteristic sort of was that allowed us to go from square to square on the chessboard. It would also be helpful to take a look at just the general form of an exponential function and ask yourself, okay, what do I notice about the form of the function? What is happening every time x increases by 1? And also to think about our discussion with regards to rate of change. How does the rate of change of an exponential function behave? And can you see that in the data here? And hopefully that will help you to come up with a couple of different descriptions. We'll go ahead and take a look at it together very shortly. Okay, so if I'm taking a look at the general form of an exponential function, a b to the x, and this is a very simplistic form. Notice we don't have any coefficient up here, no c value. What I notice, of course, is that the base is what I'm going to be multiplying by a certain number of times, or x number of times. And so if I increase x by 1, I expect to multiply by another value of the base, whatever the base happens to be, which is why doubling can be written 2 to the x. So when I'm looking at the outputs here, I expect to be seeing that I multiply by some value each time the input increases by 1. So I should be multiplying by the same value to go from here to here, and then the same value to go from here to here. In other words, the growth factor. So I can look to see that that is the same as I go from output to output. So how can I test this out? Well, what would I need to multiply 7 by to get 21? Or in other words, what's 21 divided by 7? And that is 3. And hopefully it's about the same to get me from 21 to 63. And sure enough, it's exactly the same. And 63 to 189, again, is multiplication by 3. So that's one way that I can see that this is data that would be modeled really well, in fact, perfectly well, by an exponential function. But there's another way that I can figure this out. Remember that the rate of change of an exponential growth function will increase as the domain increases. So if I compute the average rate of change between, for example, 0 and 1, and the average rate of change between 1 and 2, and the average rate of change between 2 and 3, I should be seeing that average rate of change increasing. And if it's increasing, that's a good hint that an exponential function would be a great function to model this data with. So let's go ahead and do that. I'm actually going to add on another column to the table here. And I'm going to compute the average rate of change. So why don't you go ahead and pause the video and try this yourself. We'll find the average rate of change between 0 and 1, the average rate of change between 1 and 2, and the average rate of change between 2 and 3. Alright, so let's start with the average rate of change between 0 and 1. The difference in the y values is 21 minus 7. And the difference in the x values is 1 minus 0, and so that is going to end up being 14 over 1, or 14. The average rate of change between 1 and 2, the difference in the y values is going to be 63 minus 21. Difference in the x values, again, is 1 minus 0. 63 minus 21 is going to be 42, and so I'll have an average rate of change of 42. Between 2 and 3, I have 189 minus 63 as the change in y, divided by the change in x, which is 1 minus 0. And here, 189 minus 63 is going to be 126. And so I can see that the average rate of change is increasing over the domain, which is one of the key characteristics that we see with an exponential function. And so both of these key characteristics are visible in the data set, and therefore I think it would be a good idea to use an exponential function to represent this pattern in the data. So let's go ahead and capture these two key points so that when we're looking at a data set, we can make a decision or a determination on whether to use an exponential function to model the data. Alright, so we've discussed this before, that when we collect data or we have a set of data, we want to look for the pattern in that data so that we can use the pattern to make predictions about data points that we don't have. And this is nothing more than creating a function, which is exactly how we write out the pattern. And once we have that function, we can use it to make predictions. And so that's why we're going through this effort here. For an exponential model in particular, what we just noticed is that the ratio between output values should be consistent. And what we mean by that is exactly what we saw in the discovery problem. When we're going from output to output, we should be multiplying by about the same value each time, right? The growth factor should be consistent. Now, when we have data, it's not going to be perfect, right? So we're not going to have the exact growth factor for each output, from output to output. So when we say consistent, we mean approximately the same. One other thing to be mindful of is that when you're looking for this growth factor or the ratio between output values, you want to make sure that you're paying attention to how the x values are changing. For example, as we saw in the discovery problem, where if we notice that the x values are always changing by 1, then we're expecting to always be multiplying by the same growth factor. But if you notice that the x values are changing by 1, and then maybe they start changing by 3, you should adjust what the ratio you expect will be appropriately. Let me give you an example of this. So let's say that we have a table of values here, just like we had previously. 0, 1, and then it goes to 3 here. So if we have 7 and then 21, instead of 63, what we'll have is 189. And so when we're computing the ratio between the outputs, if we go from 7 to 21, we'll notice a growth factor of 3. But from 21 to 189, we'll notice a growth factor of 9. And that should be expected because we had to make 2 jumps in the x direction. The x value changed by 2, and so we'd expect to multiply by 3 twice. In other words, multiply by 9. The good thing is that we don't always have to compare the ratio between output values. We also noticed that the average rate of change is a key characteristic that allows us to see the pattern in the data. So for exponential growth, what we're expecting to see is an average rate of change that is positive and increasing quickly. That's what we saw in the discovery problem. If we have an exponential decay function, and let's just quickly graph what that might look like. What we expect is for the average rate of change to decrease and to approach 0. And we also expect it to be negative, right? Here the function is decreasing always. So what we have is a negative average rate of change, and we expect it to be getting closer to 0. So if we're computing the average rate of changes, that's what we're looking for to determine whether an exponential decay model would be appropriate. Alright, so let's go ahead and try a couple on our own. Alright, so here we have 3 data sets, and for each data set, your goal is to determine whether an exponential or a linear model is most appropriate and justify your answer. So real quickly, before you get started, make sure you remind yourself what kind of key characteristics a linear model has. Think carefully. It is the constant rate of change. That's what a linear model is defined by. And we just talked about the key characteristics that allow us to determine whether an exponential model works, and you are more than welcome to use either one, either looking at the ratio between output values or looking at whether the average rate of change is increasing quickly, if it's an exponential growth function, or decreasing and getting closer to 0 if it is an exponentially decaying function. And for these examples, you don't have to worry too much about what each of these tables is representing. We're actually going to talk more about the context of these situations in class. So your goal is just to determine whether exponential or linear makes the most sense. Be ready to justify your answer, so make sure you have your justification for each one so that you can confer and confirm with your teammates.